The Greek philosopher Zeno made a very interesting argument. He said, let a hare be raced against a tortoise. Now, you might think that the hare will always win because it runs so fast, but Zeno said, consider the following situation. The tortoise is given 100 meters lead. The hare starts running after the tortoise. But by the time that the hare has reached 100 meters, the tortoise has moved on. And so the hare has to cover that distance. But by that time, the tortoise has moved on still further. And so it goes. Therefore, the conclusion is that the hare can never overtake the tortoise. Or take another argument, more common one. Let's say that there is a bus which is standing and you are running after the bus. Well, first, you cover half the distance. There's still half the distance left. You cover half of that, but then there's still 1/4 left. So you have to run that, and then you have to run 1/2 of that again, and so forth. And so if you follow this logic, you will never catch the bus. This is called Zeno's paradox, and this encourages us to think about infinite sequences and then infinite series. Let's begin with the notion of a sequence. A sequence is just a collection of numbers which are ordered. So A1, A2, A3, A4, etc. This forms a sequence in which A1 comes first, A2 second, A3 third, A4 fourth, and so forth. There's a common notation to denote a sequence, and that's curly brackets AN. N here runs from 1, 2, 3, all the way up till infinity. In other words, it never stops. There are countless examples of sequences that one can give. Here is a constant sequence in which you have simply 1, 1, 1, 1, 1 all the way through. And in this case, AN would be just 1 itself. So each member of the sequence is 1. You could have 1, then 4, 9, 16, and so forth, in which case AN would be n squared. So this sequence stays constant, this sequence increases. On the other hand, you could have a decreasing sequence. You could have 1, 1 over 2, 1 over 3, 1 over 4, and obviously this sequence has every element as 1 over n. You could have a sequence that constantly changes its sign. So 1, minus 1, then plus 1, minus 1, plus 1, etc. In which case, AN would then be minus 1 to the n plus 1. Of course, the absolute value of AN remains just 1. You could have an alternating sequence. So this over here is called an alternating sequence. That's alternating because the signs are alternating. But another alternating sequence would be 1 minus 1 over, let's say, 2, 1. So now plus 1 over 4, minus 1 over 8, and so forth, in which case AN would then be minus 1 to the n plus 1, but it would be divided by 2 to the power n. Now these are all examples where AN has been given to us. Sometimes looking at a sequence, we have to guess what AN is. Look at this sequence. Here A1 is square root of 2. A2 is square root of 2 plus square root of 2. And then here it becomes more complicated. A3 is the square root of 2 plus square root of 2 plus square root of 2, and all of this written in this form. and so forth. Here's A4. And now you can guess what A5 is going to be. But the question is, can we find a formula, AN equals something, that'll give us this sequence that we see over here? Well, let's try and guess that. So, let's write A1 as 2 to the power half. That makes it a bit easier than the square root sign. Then A2 is 2 plus 2 to the half, and that is to the power half. But then this 2 to the half is really A1. So let me write this as 2 plus A1 to the half. Now let's come to the third one. In this case, A3 is 2 plus what to the power half? Obviously, it's this thing, square root 2 plus square root 2 inside, and that's A2. And so you see there's a pattern that's come out, that A2 is 2 plus A1 to the half, A3 is 2 plus A2 to the half, and so that suggests that AN plus 1 will be 2 plus AN to the power half. In other words, the next A is related to the previous A through this formula. Now, this here is an example of a recursively defined sequence. In other words, what happens here is that the previous value, AN, defines the next value, AN plus 1. So you can check that every term of this sequence can be got by this formula. Next, let's look at this sequence here. 2, 2 plus 1 over 2, 2 plus 1 over 2 plus 1 over 2, and so forth. It gets too complicated to put in words. But it's always 2 plus 1 over something. Okay, so let's write A1 is 2. A2 then is 2 plus 1 over 2. But this 2 I will write as A1. Well, let's go to this one over here. That's A3. A3 is 2 plus 1 over, now 2 plus a half. But 2 plus a half is A2. So A3 is got from A2 in this way. So A3 is got from A2 just as A2 was got from A1. But of course you had to start with something, and A1 was given to us. Now from here, obviously the generalization that we can make is that AN plus 1 is 2 plus 1 over AN. And now this is the recursion formula for this sequence here. And now let's look at this sequence here. A to the power A to the power A to the power A, and it keeps going. Here, A is any number. And we can't, by just looking at this, say whether this is a decreasing or an increasing sequence. It'll depend upon the value of A. But anyway, let's try and get a formula for this. So A1 is A, then A2 is A to the power A, but A1 is A itself. So we've got A2 in terms of A1. Let's look at A3. A3 is A to the power A to the A. So here we have A to the power A2, and now it's pretty clear that AN plus 1 should be equal to A to the power AN. And so the recursion relation for this sequence over here is got over here. Now, we've got these three recursion relations. They are going to help us decide what happens to this sequence, or this sequence as n becomes larger and larger. Will this all go somewhere or will it blow up? We'll find that out soon. Here's the formal definition of an infinite sequence of real numbers. What this is a function whose domain is the set of positive integers. What that means is the following, that instead of writing a sub n, instead of labeling every element of that sequence in this way, we could equally well write it as an. A as a function of n, where n is 1, 2, 3, and has no limit. It belongs to the domain of positive integers. Now, we could have earlier on written a of n as n squared, or we could have written a of n as minus 1 to the n over, let's say, n. And this would have been perfectly okay, although we had written an was n squared and an was minus 1 to the n over n. But the point is that this and this are completely equivalent, as of course are this and this. The fact that every element of this infinite sequence can be got from a function with different values of the argument n is something that's going to be very useful for us. The fact that a sequence is actually a function of the integer n makes it possible to graph it and to visualize it more easily. So let's take this sequence Cn, whose every member is given by 1 plus 1 over 1 plus n squared. Let me put n equal to 1, then 2, 3, 4, 5, 6, 7, and you see that this sequence is tending towards 1. So it's tending to that line which you see. Now what if I was to plot the function f of x equals 1 plus 1 over 1 plus x squared? Here's that function plotted, and you see it goes exactly through those points of the sequence. Let me repeat with another sequence. And here I'm going to take the sequence an, where each an is given by this formula over here. Now I'll put n equal to 1, 2, 3, 4, 5, 6, and 7. I'll now plot this function. G of x is 3 over 3 plus 100 e to the minus 2x. So this function f of x and this function g of x, you can see are both converging to the constant value 1. And similarly, the sequences are converging to the value 1 as well. Now in this simple case, where n tends to infinity, certainly Cn will go to 1, like this, and here an, as n tends to infinity, will go to 3 over 3 plus what's essentially 0, so an is also going to 1. Here you have the case of two sequences which are converging to the same final limit. What happens to a sequence as we go further and further along it brings us to the question of convergence and divergence. Let me give many examples, beginning with this ridiculously simple sequence 1, 1, 1, 1, 1, and an is 1. Now, this is an example of a convergent sequence, because even if we go very far away, we are still going to get 1. Next, let me take this 1 over 2, 1 over 3, 1 over 4, and so forth. So an is 1 over n. Again, this is convergent. And that's because as n becomes larger and larger, we're going to get closer and closer to 0. So this sequence here is said to converge to 0. Here's an example of a divergent sequence. 1, 2, 3, or let's say 1 squared, 2 squared, 3 squared, 4 squared. And in this case, we have an is n squared, and this is a divergent sequence. It blows up. There is no limit as n goes to infinity. Of course, it could go to minus infinity. So let's say that we have minus 1, minus 2, minus 3, and so forth, in which case an is minus n, and then that is again divergent. You could have something that is divergent for other reasons too. So, for example, if you have plus 1, minus 1, plus 1, minus 1, etc., in which case an, as we've discussed before, is minus 1 to the n plus 1. This is also divergent because this sequence simply keeps alternating. Although it does not go to either plus infinity or minus infinity, yet it does not tend to any definite number. Let me now give a formal definition for the convergence of a sequence. Here's that definition. A sequence an is said to converge to L for limit, if for any epsilon, and this epsilon is going to be very, very small, there can be shown to exist a number n, so n is going to be some large number, such that an minus L, the absolute value, is less than this epsilon, provided that n is bigger than this n over here. Now, this sounds very abstract. You've got to read this again and again to see what it actually means. But here is what it means. So we'll take our sequence as points, and let's say they're going to get closer and closer until they start approaching this limit, which we'll call L. So here is the limit L, which I've drawn with a cross over here. And now the points are going to get closer and closer and closer, and then I will not be able to draw them. So the point is that an is going to get very, very close to L. So it's going to become less than epsilon, or we're going to say that an is approaching L. Both of these are the same, but this is a more precise way of saying this. It's more precise because instead of simply saying that an is approaching L, we are saying that a value of n can be found such that this number over here is as small as you like. Remember, it is for us to choose epsilon. We could choose it as 10 to the minus 6, so that's an accuracy of 1 in a million, or we could choose it as 10 to the minus 12 or anything that you like. The point is that once you choose this epsilon, then there has to be an n such that if you exceed this, then an minus L is less than this very, very small number. Now let's use this definition of convergence to prove rigorously, mathematically, that this sequence, which is given over here, converges to 0. Now let's begin by writing an in a slightly different way. So I'm going to write this as square root of n plus 1 minus square root of n, and I'm going to multiply this by square root of n plus 1 plus square root of n divided by the same. So just multiplying and dividing by the same number. The advantage of that is clear because then I have just n plus 1 minus n divided by the square root of n plus 1 plus square root of n, and that's 1 over this thing, square root of n plus 1 plus square root of n. So far, I've done nothing except write an in a different way, that is 1 over square root of n plus 1 plus square root n. Now what I want to do is show that the limit L equals 0 is approached by an. So suppose we take an minus L, the absolute value of that. Well, since L is 0, that's 1 over the square root of n plus 1 plus square root of n. And now, if that is equal to epsilon, let's see what value of n will give us this. Let's solve this. And so we need to solve square root of n plus 1 plus square root of n equals 1 over epsilon. Now, since n is going to be very large, so I might as well write this as 2 times square root of n is equal to 1 over epsilon, in which case n is 1 over 4 epsilon squared. Now, the smaller the value of epsilon, the larger the value of n I will have to take. But the point is that no matter how small epsilon is, I can always find a value of n such that this is equal to epsilon. And if I take a value of n which is bigger than that, then I will have satisfied the condition that an minus L is then less than epsilon. So this proves to us that this sequence over here converges to 0. Before I say anything else about the convergence of sequences, here are some words that you need to know, because if you read any textbook on calculus, you're certainly going to encounter them. First, a sequence A1, A2, A3, A4, etc. is said to be bounded from above if any member of the sequence, let's call that an, is less than or equal to some number m. Now this number m over here, I'm not saying what that is. It could be 5, it could be 5 million, it could be 5 trillion, but it has to be a finite number, else this sequence will go to infinity. So if we were to make a little graph like this, then our sequence could be going like this, let's say coming down like this, whatever. But this sequence will be bounded if it never exceeds this number m. Now, this sequence will be bounded from below if a certain obvious condition is fulfilled. And you can easily write that as an is greater than or equal to minus m. And this m don't have to be the same. And what that means is that our sequence could go like this, maybe, and come down like this. But if it is bounded, it will never go below this over here, minus m. And again, I say this m and this m don't have to be the same. Next, a sequence A1, A2, A3, A4 is non-decreasing if an plus 1 is greater than or equal to an. So the next member is bigger than the previous member. And so this is a sequence, let's draw it over here, that's either going up So that's the case where an plus 1 is strictly greater than an, or that sequence could be simply a constant sequence. In both cases, this is going to be called non-decreasing, and that's pretty obvious because it's not decreasing. After this, it should be no surprise that a sequence A1, A2, A3, 4 is called non-increasing if an plus 1 is less than or equal to an. And so what that's saying is that the members of the sequence are decreasing in size as n increases. So it's the opposite of what you saw above. Here is a non-increasing sequence. Its members are decreasing, or it could be, as before, that all the members have the same value. And so this is for the case where it is strictly decreasing, and here where it is a constant. So for both of these cases, we say that this is a non-increasing sequence. And finally, here is a fancy word. A sequence A1, A2, A3, A4 is called monotonic if it is either non-decreasing or if it is non-increasing. So either this condition or this condition is enough to make it monotonic. Now what does that mean? It means that this is fine. This is a monotonic sequence. This is a monotonic sequence because it is constant. So it is the equality sign in either this or that. Or it could be this, which is a decreasing sequence, and this too is monotonic. On the other hand, this sequence, which I'm now drawing in blue, which is like this, it goes up, it comes down. So this is definitely not monotonic. The red ones are all monotonic, but the blue one sometimes increases and sometimes decreases, and hence is non-monotonic. I'm now going to describe a set of very useful tests that will allow us to decide whether a sequence actually converges or if it does not. First, let's understand this test. Here we have three sequences. Sequence A with elements A1, A2, A3, etc. Sequence B and sequence C. We are told over here that B lies between A and C. What that means is that every element of the sequence B is sandwiched between an element of the sequence A and the sequence C. Further, we are told that as n becomes larger and larger, the sequence A tends to L, and similarly the sequence C tends to L. If these conditions are satisfied, then the limit of the sequence B is also going to be L. Let's first draw a little picture of this. So here is the sequence A. This is A1, A2, A3, A4, etc. And here is the sequence C. So C1, C2, C3, C4. And now they're clearly tending towards the same limit. That limit is L, whatever that L is. If there is a sequence that lies in between them, so let's say that B1 is this one, B2 is, let's say, this one, B3 is over here, and B4 is here, and now it's getting hard for me to draw, but you get the picture that B1 lies between A1 and C1, B2 lies between A2 and C2, B3 lies between A3 and C3, and so forth. So if sequence A is tending to a limit and sequence C is tending to that same limit, then B is forced to lie in between A and C, and so it too will go to the limit L. One can give a formal proof of this using the definition of convergence with the epsilons and the n's, but that will take too long. Instead, let me go on to the next test. This says that if a sequence is bounded, which means it doesn't go to positive infinity or negative infinity, furthermore, that it is monotonic. We know what monotonic means. That means it goes either strictly upwards or strictly downwards, or it remains constant. So if it is both bounded and monotonic, then it must converge. Now let's think about this a little more deeply. A sequence can be bounded and yet not converge. So for example, if I had -1 to the n plus 1, now this would fluctuate as 1, -1, +1, -1, +1, -1, etc. So it would be bounded, but this would not converge. A sequence can be monotonic. So for example, the sequence n squared, or rather, here I should say an is equal to this and an equals this. This is certainly monotonic, but it does not converge. But if a sequence is both bounded and monotonic, then it must converge. It will converge. Here is an example of that. The sequence A1 is both bounded and it is monotonic. In fact, it's strictly decreasing. And it is converging. Look at the sequence C. This is also monotonic. It's strictly increasing. And it is also bounded. And of course, it is converging. Again, the formal proof of this is easy, but I'm not going to do that. Here's a third very useful criterion. It says, if the function f of x has the limit L at x equal to infinity, then provided that an is f of n, and remember that this an actually means a of n. So a is a function of the number n, the integer n, and this a and f are of course the same. Then the limit as n tends to infinity of an is also L. Now that too is pretty obvious, and it's actually going to be very useful. So now let's go and look at some examples. Let's now work out a few examples quickly. First, does the sequence an with an 1 plus 1 minus 1 to the n converge or diverge? Well, it's pretty obvious that we have a1 is 0, a2 is 2, a3 is 0, a4 is 2, and so forth. So 0, 2, 0, 2, etc. So the answer is no. It does not converge. What about this? Does the sequence Bn with Bn equal to this converge or diverge? We can answer this using that sandwich test that we just discussed. So let's define an to be 1 plus 1 over 2n plus 1 and cn to be 1 minus 1 over 2n plus 1. In that case, Bn then gets sandwiched in between these. So it's lesser than or equal to an and greater than or equal to cn. Now, you can see that an goes to 1 as n goes to infinity. That's clear from here. And cn goes to 1 as n goes to infinity, and you can see that from here. And so from these, we deduce that Bn also goes to 1. And so it certainly converges. Yes. Next, does this sequence an, where an is n factorial divided by 2 to the n into 3 to the n, converge, or does it diverge? Well, let's first write an in a slightly simpler way. We'll write it as n factorial divided by 6 to the power n. As n becomes larger and larger, certainly n factorial becomes infinity. But of course, 6 to the power n also becomes infinity. So how are we going to decide what this infinity over infinity is? Let's do the following. Write n factorial in the following way. N into n minus 1 into n minus 2, etc., all the way up till 7, then 6, 5, 4, 3, 2, and 1. This has to be divided by 6 to the power n, which means we've got to have 6 here, 6 here, 6 here, and then 6, 6, 6, 6, until the last one here. So, now we have a product of 6's below and a product of integers up above. Let's separate this into two parts. So, there's this part until 7, and then there's this part after 7. Now, this is some number. I don't care what that is. It's some number which is less than 1. But this here is a number that goes to infinity as n becomes larger and larger. And you can see that because each one of these numbers is bigger than 1. So n over 6 is bigger than 1, so is n minus 1, and 7 over 6 is also bigger than 1. So you're multiplying an infinite number of numbers, and that's infinite because n is going to infinity, and so therefore this diverges. This sequence does not have a limit. Next, let's look at the sequence an, where an is log of 1 plus 1 over n to the power n. Does this converge or does it diverge? The logarithm is a monotonically increasing function of its argument. So let's look at the argument, which is 1 plus 1 over n to the power n. Looking at the first few terms, so we have 1 plus 1 over 1 to the 1. The next term is 1 plus 1 over 2 to the 2. Then 1 plus 1 over 3 to the 3. This is not telling us very much. Is it increasing, decreasing? What is it doing? Instead, let's look at a function f of x, which is 1 plus 1 over x to the power x. Now clearly, this over here and this over here are the same if x is equal to n. But this form over here will allow us to get the limit as x tends to infinity, this being a continuous function. Now, if you remember, any number to the power x can be written as e to the x log of b. To check this, just take the logarithm of both sides. So here, what we have is e to the x log of 1 plus 1 over x. But as x goes to infinity, 1 over x becomes smaller, and log of 1 plus 1 over x, this becomes closer and closer to 1 over x, and then there are terms minus 1 over x squared and so forth that we will not need to keep. So this is e to the power x, and then 1 over x plus terms that we disregard. This is, of course, e. And hence, an, which is the logarithm of e, this is as n goes to infinity, this is then 1. And so the limit as n goes to infinity is an goes to 1. So I should really write it as this. And so this sequence then converges. Consider now this sequence a to the a to the a to the a, and so forth. The question is, will this sequence converge, and for what values of a? We can define this sequence recursively. Earlier we saw that we could write it as an plus 1 is equal to a to the power a sub n, together with the condition that a1 is equal to a. So a2 then will be a to the power a1, which is a, and so forth. Now, let's assume the convergence of this sequence. And this assumption will then make it possible to see for what values of a this assumption is justified. If it is assumed to converge, what that means then is that the limit of an as n tends to infinity must be some finite number, call it c. Okay? In that case, that says that there should be no difference between an plus 1 and an, since it's converging, and so therefore c should be equal to a to the power c. This is very important to realize. What I've done is I've just put an plus 1 equal to c and an equal to c. Now take the logarithm of both sides, so we get from here the logarithm of c is equal to c log of a, and hence we have then log of a is equal to log of c divided by c. Now, and you could of course also write this as a is equal to e to the log of c over c. In order to understand what log of c over c is doing, let's plot the function f of x equals log of x divided by x. Now immediately we can see some things about this. When x is 1, this function is going to be 0 because log of 1 is 0. As x goes to infinity, f of x is going to go to 0, and so it has to go up before it comes down. Let's see the maximum value it reaches. So if I calculate f prime of x, first I differentiate log of x, I get 1 over x, so there's 1 over x squared. Then I differentiate 1 over x, so I get minus log of x over x squared. And if f prime of x is set equal to 0, then clearly log of x must be equal to 1, and so x will be e, and of course f of x then will be log of e, which is 1, divided by x, which is e. So therefore this is a function that goes up and then comes down, and the most it goes up, its peak value will be 1 over e. So this is saying that the log of c over c at most is 1 over e. And of course from log of a equals log of c over c, you immediately get a is equal to e to the 1 over c log of c. Now 1 over c log c has to be less than 1 over e, as we've discovered over here, in which case a has to be less than or equal to e to the power of 1 over e. On the other hand, a has to be bigger than or equal to 1, because when we're at this point over here, log c over c is 0, and then log of a is 0, which means a is 1. And so there is a range of values of a that's given over here for which this sequence will indeed converge. We've seen plenty of sequences so far. of all different kinds. They're all of the form A1, A2, A3, A4, etc. And this never stops. We denoted this with AN. Now, I'm going to make something a little different by adding up all these numbers. S1 will be plain A1. S2 will require adding A2 to A1. S3 will be A1 plus A2 plus A3. And I can keep going. In fact, I can write Sn as A1 plus A2 plus, and keep adding until the last member is An. And this capital N can be anything. Now, to shorten this, I'm going to write this as the sum from n equals 1 up till n of An. So this and this mean exactly the same. But you see, what I have now is now a different sequence. I have that sequence made with S1, S2, S3, and so forth. And this is exactly of this form. That is to say, this is the sequence Sn. But even though there is no last member, we do have a meaning for this thing. N equals 1 to infinity of An. And we call this the sum of the infinite series. So this over here is called an infinite series. Does it exist? Well, that'll depend upon An. For some kinds of sequences, you can add up the numbers and this S will exist. In other words, there will be a convergence of the sequence S to this number. And only if that convergence exists, then we shall say that the infinite series exists, or that infinite series converges. To understand infinite series better, let me go back to Zeno's paradox with which I had begun the lecture. So here's a man who's running to catch this bus, and here is the sequence of distances. First, he runs 1 unit, then half of that, then half of that again, so 1 over 2 squared, then half of that again, 1 over 2 cubed, and so forth. So he covers 1 unit of distance, then half unit of distance, then half of that, and then half of that, and he keeps going. The question is, how much distance will he cover? Will it be enough to catch the bus? And so, this being our sequence An, let me make S1, S2, and so forth. So S1 is 1. S2 is 1 plus a half, which is 3 over 2. S3 then will be 1 plus a half plus 1/4, and this is 7 over 4. S4 will then be 1 plus a half plus a quarter plus 1 over 8, and you can easily calculate that to be 15 over 8. S5 will be, then you add all of these and you get 31 over 16, and now there's no space left over here. The point is that we're getting closer and closer to 2. So Sn, which is n equals 1 up till n of An, now An over here is 1 over 2 to the power n minus 1, is getting closer and closer to 2. But this is as n tends to infinity. However, we have not proved this. It is only suggestive because, yes, 31 over 16 is very close to 32 over 16, which is 2. But already we are seeing that the convergence of a series is no different from the convergence of a sequence. Because a series like this actually forms a sequence.
By now, we've certainly realized that Zeno's paradox isn't really a paradox, that certain sequences and series converge while others diverge. We also decided upon the criterion by which we can decide whether a sequence or a series converges or diverges. But these are not enough, and so we will continue this in the next lecture.